All right, we're attempting to revisit my video on trapezoidal rule and Simpson's rule. So just finishing working through trapezoidal rule, we have 1/2 times when we add all these numbers up, we get 96. So our trapezoidal area approximation is 48. Remember, it's just an approximation. When we do an approximation for Simpson's rule, instead of a 1/2, we'll have a 1/3. Our interval width is still 1. And then this time when we list out our y values, we list out 1, and then 4 times 3, and then 2 times 9, 4 times 19, and then just 133. So remember, we're using this pattern from up above, from Simpson's rule. 1, 4, 2, 4, all the way until we get back to 1 again. All right, and when we multiply that out, or I guess it's adding and multiplying here, the number inside our bracket is 140. And so we have 140 thirds, which is really hard to compare. So I would go ahead and go with a mixed number on this, and that's 46 and 2/3. Remember, if this was an AP test problem, all we would do is we would write this out and then we would stop, right? We don't actually go through and calculate and simplify. So to find the exact value, that's when we use calculus. So my exact value I would get by integrating. So 2x squared, remember we're going to increase our power to the third power, divide by 3, and then it's plus an x, and this is from 0 to 4. So when we substitute 4, we get 2 times 4 to the third, divided by 3, plus 4 minus, and then we would substitute 0 for both of our x's, so it's just 0. So this ends up being, let's see, 2 times 64 would be 128 thirds, plus 12 thirds is equal to 140 thirds. So just what we got for Simpson's rule. So it's really kind of cool to see how close our Simpson's rule approximation is, and really even the trapezoidal rule. It's a much better approximation than if we're using a left Riemann sum or a right Riemann sum. So we want to do the same thing again. We're going to practice one more time with trapezoidal and Simpson's rule. This time we're looking at, let's see, the integral from 0 to pi of sine x when n equals 4. So if I'm looking for my interval width, I would use pi minus 0 over 4, which is pi over 4. So then for my table, I would make that start at 0, then pi over 4, pi over 2, 3 pi over 4, and then pi. So we might need to go through and draw some triangles on this to figure out our y values. So sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0 again. Okay, and then we want to try pi over 4 and 3 pi over 4, which is going to be a second quadrant but same triangle. So my triangle, there's different ways of labeling it. I could write 2, root 2, root 2, 2. I could write 1, 1 square root of 2. There's a lot of different ways to rationalize this, but my sign ends up being 1 over the square root of 2. Because I am trying to add a bunch of y values together, I am going to use this in the rationalized form. I'm going to use root 2 over 2. I think that'll be easier. And because my y is positive in the second quadrant, my sign is the same thing, right? Because my y value is still a positive. It's still above my x-axis. So these would both be the same value. All right, so first we're going to approximate our area using trapezoidal rule. So I have the 1/2. I have my interval width, which is pi over 4. And then 0 plus 2 times root 2 over 2 plus 2 times 1 plus 2 times root 2 over 2. And I'm totally mucking up my square root there. It needs to be only on the numerator. And then plus another 0. So even though my beginning and end values are just 0, I still have to count them. Those are the values that I have one of. I'm not like just jumping to my next y value or anything. So 1/2 times pi over 4 would be pi over 8. And then inside my brackets, I would have, let's see, a radical 2 and another radical 2. So 2 radical 2 plus 2. So I could absolutely factor out a 2 and reduce this. But I really think because we're comparing answers, it's going to make more sense to have a decimal here. So when we go through and we multiply this out, we get the decimal. We have 1.896. And really, we're adding and multiplying, right? I should be saying that correctly. So it's 1.896. So area, if we use Simpson's rule instead, well, that's going to be a 1/3 instead of a 1/2. Still have the interval width. And then again, with our values, it's a 1, 4, 2, 4, 1 is what we're going to have. So 1 of the zeros, 4 of the root 2 over 2's, 2 of the 1's, 4 of the root 2 over 2's, and then 1 0 at the end. Okay, and then we're going to go through and simplify this one. So this would be pi over 12. And then inside, this would make 2 root 2 plus another 2 root 2, so 4 radical 2 plus 2. And again, I could factor out a 2, simplify that with the 12, but really what we want here is a decimal so that we can compare. And we have 2.005. So it looks like we're kind of narrowing in on 2. So now we're going to go ahead and find our exact value. Again, you could check this on a calculator, but it's really good for us to do the trig and work this out by hand. So if you get stuck on trig, one thing you can always do is go back to saying, well, I know this is cosine when I integrate, but let's just double check our signs. So if y equals cosine x, and I take my derivative, I know it becomes a negative sine x. These are different by a negative. So sometimes it's good to just take the derivative because that's the easier direction, right? That's the forwards, and finding the antiderivative is like doing the backwards. So now I know that this really needs to be a negative cosine of x from 0 to pi, and I'm going to go ahead and leave that negative outside for now. I think I'm going to make less mistakes that way. So then I've got to take the cosine of pi minus the cosine of 0. So on this one, when I have cosine of 0, I can't just ignore it and pretend it's a 0. Like if I'm doing a polynomial, right? I've got to be careful. So if I'm thinking about the cosine of pi, that's -1. So this is going to be the negative of -1 minus cosine of 0 is a +1. So I have negative of -2, which is a +2. So again, I could check with this with my calculator, but I really think it's valuable to go through and work out the trig. All right, last problem. The velocity of a particle moving along the x-axis is modeled by a differentiable function v, where the position x is measured in meters and the time t is measured in seconds. Selected values of v of t are given in the table above. Using correct units, explain the meaning of the integral from 20 to 40 of v of t dt in the context of the problem. Use a trapezoidal sum with the 3 subintervals indicated by the data in the table to approximate this integral. Okay, so first of all, when we're looking at integrating velocity, then we get like our position. So if we are adding up all those different positions, we're taking that area under our velocity curve, it's like we're finding a distance. So what we've got to decide is this one going to be a total distance or a displacement? So total distance is if I go in the negative direction 5. Instead of counting it as a -5, I'm counting it as a 5, right? So like if I start here and I go -5 units and then I go +10, when I'm doing total distance, I would say it's 15. If I'm doing displacement, I'm going to say, well, now we're at 5. So we have to decide what this is doing. So the way you get a total distance is really by taking some kind of absolute value along the way, right? You've got to take negatives and count them as positives and count up all of those total things. So that's like that difference between finding an integral and finding an area, right? Because area we always want to count as positive. So displacement is just like how far am I from the beginning. So when I look at these intervals from 20 to 40, when I look at the interval from 20 to 25 or 25 to 32 or 32 to 40, I've got some negatives mixed in there. And when I'm finding this integral from 20 to 40 of v of t dt, nowhere does it say I'm taking an absolute value or anything. So this is going to be the displacement. So this is the displacement of the particle. We want to be specific and use units in meters. From t equals 20 to t equals 40 seconds. We could also say on the interval, we could say it that way too, but because I wanted to give units, it just feels a little bit clunky to say the interval and then have, the 20 comma 40 and then say seconds afterwards. Okay, so now I want to actually approximate this using a trapezoidal rule. So I've got to go through, and because there's 3 intervals, I'm going to be finding 3 trapezoids on this. So this is not one. If you look at our interval widths, they vary from 20 to 25. Like my first one here, the interval width is only 5. The next one from 25 to 32, my interval width is 7. So like I was warning you, we have to make this into 3 different intervals. So the first one, dt, and we're approximating. So the first one is a 1/2 times my interval width is 5, and then my 2y values are the -10 plus the -8. My second trapezoid is still a 1/2. Now I'm looking at this interval right here from 25 to 32. So the interval width is 7, and my 2y values are a -8 and a -4. And then my last interval, let's see, the last interval is from 32 to 50. So that would be a 1/2 times an 8. And then my heights are from -4 to 7. And I just barely squeeze it in there. So remember, on the AP test, we don't actually want to go through and calculate something like this. This is how we make our mistakes. Usually the calculus part we do great with, but just the little simplifying errors with negatives and positives, when you have this many numbers you're working on adding and multiplying and adding again, we make mistakes. So we're just going to leave it. So this is going to be the displacement of the particle in meters from 20 to 40 seconds. We explained that what that was. And then here we have the trapezoidal sum. So we're all set. So main ideas are really how we get this trapezoidal sum, like how this makes sense. How we had this, where this part on the formula comes from, that we've got the, why my pen's not working, where we've got the 1/2 times the interval width, where these coefficients come from, what trapezoids look like, Simpson's rule. Remember, that's got the curvy top instead, so it's even a little bit more accurate, and then how to set that up. Really, the book also does some work with approximating the error from each of them. That has gone away from AP, AB land. I don't even know if it's in BC anymore. And so unfortunately, with our 4 days a week instead of 5 days a week, our new block schedule, we just don't really have the time to go over that. So I just think this is really cool how accurate we are, and I like this AP problem that gives us an idea about how you might see it on the AP test later on. As always, if you have any questions, please make sure you ask.